Welcome back to the deep dive. This time, we're going behind the scenes of a post-grad machine learning course.
Oh, cool.
Yeah, we've got the lecture notes and course outlines.
Nice.
So think of this as like your VIP pass to understanding
Yeah,
what really makes ML tick.
exactly. We're going to skip all that surface level stuff and focus on like the core concepts and the cutting edge advancements.
Right.
The stuff that makes this field so exciting.
Okay.
It's about understanding how ML is not just changing technology, but like changing the world.
All right. Let's dive in. This first lecture jumps right into foundational concepts,
Right.
like the difference between supervised and unsupervised learning.
Yeah.
It's like laying the groundwork
Huh.
for everything else we're going to explore.
Yeah. Supervised learning is like teaching a machine with labeled examples.
Okay.
Like you show it a bunch of pictures of cats and dogs,
Yeah.
telling it which is which,
Uh-huh.
and it learns to identify new pictures on its own.
So it's all about predicting outputs based on what it's already seen.
Exactly. But then we have unsupervised learning,
Okay.
which is more about letting the machine discover hidden patterns on its own.
Mm,
Imagine giving a child a box of Legos
okay.
of different colors and shapes
Uh-huh.
and letting them figure out how to group them together without any instructions.
Right.
That's kind of like clustering in unsupervised learning.
Okay. That makes sense.
Yeah.
But there's also reinforcement learning where the machine learns by trial and error,
Yeah.
like a robot navigating a maze, right?
What's fascinating is that the notes actually highlight a shift
Oh, yeah.
happening in the ML world,
Uh-huh.
moving away from something called manual feature engineering.
Right. It's this really cool concept called representation learning.
Oh.
Think about it. Instead of us like painstakingly telling the machine exactly what features to look for in the data,
Right.
we're now letting the algorithms discover those features themselves.
Wow.
It's a total game changer,
Okay.
especially when you're dealing with things like images and text.
So it's like teaching the machine to see patterns
Right.
that we might not even notice ourselves. That's incredible.
Yeah.
But the notes also talk about model evaluation metrics,
Uh-huh.
like accuracy, precision, and all that.
Yes,
I'm guessing that's how we know if our model is actually any good.
exactly.
Yeah.
It's like our scorecard,
Okay.
telling us how well our model is doing its job.
Right.
We need to be able to assess its strengths and weaknesses, and that's where these metrics come in.
Gotcha.
One of the biggest things these notes emphasize, though, is the importance of high-quality data.
Oh, for sure.
They say garbage in, garbage out.
Absolutely.
Yeah.
So what are some of the things we need to be aware of when it comes to the data
Right.
we're feeding our models?
Well, for starters, we need to be very aware of potential biases in the data.
Right.
Biases can lead to all sorts of problems,
Uh-huh.
like unfair or discriminatory outcomes.
Yeah.
It's a whole field in itself, really.
It sounds like it. Then there's the whole world of software and hardware
Right.
that makes all this ML magic happen.
We're talking TensorFlow PyTorch GPUs.
Yes.
It's like learning a whole new language.
It is a lot to take in,
Right.
but think of them as your tools.
Okay.
Each one has its own strengths and weaknesses depending on what you're trying to achieve.
Hmm.
It's all about choosing the right tool for the job.
Okay, lecture 2 takes us into the world of optimization and generalization.
Right.
Talking gradient descent
Okay.
and its variations,
Yeah.
like SGD momentum armsprop.
Yeah.
It's enough to make your head spin?
It can feel overwhelming,
Right.
but imagine trying to find the lowest point
Yeah.
in a vast, multidimensional landscape.
Whoa.
These algorithms are like our guides,
Okay.
helping us navigate that landscape efficiently and find the best solution,
Right?
which in this case is the optimal set of parameters for our model.
That's a really helpful way to think about it. But wait, the notes also mention regularization techniques.
Uh-huh.
What are those all about?
Well-
And what is this bias variance trade-off they keep talking about? It sounds a bit like walking a tightrope.
You're right. It's a delicate balance.
Okay.
Regularization techniques are like our safety net,
Right.
preventing our model from becoming too specialized to the data it's seen
Uh-huh.
and helping it generalize to new data.
Okay.
The bias variance trade-off is all about finding that sweet spot
Right.
between a model that's too simple
Yeah.
and one that's too complex.
Wow. This is getting deep. It sounds like optimization and generalization are crucial
Yeah.
for making sure our models don't just learn, but learn effectively
Right.
and can actually be useful in real-world situations.
Exactly. It's about ensuring our models are ready to handle the complexities of the real world.
Okay.
Now, lecture 3 is where things get really interesting. It's all about unsupervised learning.
Okay.
Think clustering, dimensionality reduction, anomaly detection.
Mm.
It's like discovering hidden treasures in a mountain of data.
Okay. I'm intrigued. Tell me more about this hidden treasure hunt.
All right.
What kind of gems are we talking about?
Well, let's start with clustering.
Okay.
Imagine trying to group similar data points together
Right.
without any labels.
Oh.
It's like sorting a jumbled box of objects into meaningful categories based on their similarities.
So how do we even begin to do that
Yeah.
without any labels to guide us?
We use clever algorithms like k-means hierarchical clustering and DBS scan.
Hmm.
Each one approaches the problem a bit differently,
Okay.
but they're all designed to uncover those hidden groupings in the data.
And what about dimensionality reduction? That sounds a bit sci-fi.
It might sound complex,
Right.
but think of it as simplifying a really complicated map.
Okay.
Imagine trying to visualize a data set with hundreds or even thousands of features.
Yeah.
It's just too much for our brains to handle.
So dimensionality reduction helps us make sense of that complexity.
Exactly. Techniques like PCA, TSNE, and UAMAP allow us to reduce the number of features while preserving the most important information.
Okay.
It's like creating a more manageable and interpretable map of the data.
And then we have anomaly detection, which sounds like we're getting into the realm of digital detectives.
Anomaly detection is all about finding those data points that just don't fit in with the rest.
Interesting.
Think of it as spotting outliers.
Yay.
Those unusual data points that might signal something important or require further investigation.
So it's like having a digital detective on the case, sniffing out those unusual suspects.
Precisely. We've got methods like one-class SVM isolation forest
Okay.
and even autoencoders to help us with this task.
Okay. So we've got clustering for grouping similar data points.
Yeah.
Dimensionality reduction for simplifying complex data.
Right.
And anomaly detection for finding those outliers.
Mm-hmm.
This unsupervised learning stuff is pretty amazing.
It is.
But the notes also introduce something called representation learning and autoencoders.
Yeah.
What exactly is a representation in this context?
Imagine you're trying to explain a complicated concept to someone.
Okay.
Instead of giving them every single detail, you'd probably try to capture the essence of the idea in a more concise and meaningful way.
Uh-huh.
That's kind of what a representation is.
Gotcha.
A way of encoding information about the data in a more useful form.
And autoencoders are neural networks designed to learn these representations.
Exactly. An autoencoder consists of two parts,
Okay.
an encoder and a decoder.
Gotcha.
The encoder takes the input data and maps it to a lower dimensional latent representation, kind of like creating a condensed version of the information.
Right.
Then the decoder takes that latent representation
Uh-huh.
and tries to map it back to the original input space,
Okay.
effectively reconstructing the input.
So by training the autoencoder to reconstruct its input, we're essentially forcing it to learn
Right.
a more meaningful representation of the data.
That's pretty clever.
Yeah.
I'm seeing different types of autoencoders mentioned here.
Sure.
Undercomplete, denoising, variational. Are these like different flavors of the same concept?
You could say that.
Each type of autoencoder has its own unique characteristics and is better suited for certain tasks.
Right.
Undercomplete autoencoders, for example,
Mm-hmm.
force the network to learn a compressed representation by squeezing the information into a smaller space.
Mm.
It's like trying to fit a lot of information into a smaller suitcase.
Right.
You have to be selective about what you pack.
So it's like forcing the network to learn the most salient features,
Exactly.
the ones that are essential for reconstructing the input.
Then we have denoising autoencoders,
Okay.
which are trained to reconstruct the input from a corrupted version. It's like learning to read a text message with typos.
Oh, right.
You have to learn to ignore the noise and focus on the underlying message.
That's a great analogy. So denoising autoencoders learn to extract robust features
Right.
that are less sensitive to noise or variations in the input.
Exactly.
What about variational autoencoder?
Variational autoencoders are a bit more complex.
Okay.
They learn a probabilistic latent representation, which means that they're not just learning a single representation,
Right.
but a distribution of possible representation.
Interesting.
This allows us to generate new data samples that resemble the original data.
Wow, that's really cool. So it's like learning the underlying structure of the data, the
Yeah.
rules that govern how the data is generated.
Exactly. Variational autoencoders have become powerful tools for generative modeling,
Right.
allowing us to create new images, text, music, and even more.
Autoencoders seem incredibly versatile. They can be used for dimensionality reduction, feature extraction, anomaly detection,
Yeah.
and even generative modeling.
Right.
It's amazing how a single architecture can be adapted for so many different tasks.
It is, and they're just one example of the incredible power of representation learning.
Right.
Now let's talk about another fascinating approach that leverages unlabeled data for representation learning.
Okay.
Self-supervised learning.
Self-supervised learning. That sounds intriguing. It sounds like the model is somehow teaching itself.
In a way, it is.
Uh,
Self-supervised learning is a clever way to train models without relying on explicit labels.
hmm.
We essentially create pretext tasks that force the model to learn meaningful representations from the data itself.
So it's like we're giving the model a puzzle to solve, and in the process of solving it, it learns something useful about the data. I remember the examples you gave earlier, contrastive learning and masked language modeling.
Exactly. In contrastive learning,
Okay.
we train the model to distinguish between similar and dissimilar data points.
Right.
Kind of like showing a child two pictures and asking them whether they're the same or different.
Right.
By doing this repeatedly,
Mm-hmm.
the child learns to recognize the features that distinguish different objects.
And in masked language modeling, we hide some words in a sentence and train the model to predict the missing words.
Right.
This forces the model to learn about the relationships between words and the context in which they appear.
Precisely. These self-supervised tasks encourage the model to learn about the underlying structure and relationships within the data, even without explicit labels.
Self-supervised learning sounds incredibly powerful. It allows us to leverage vast amounts of unlabeled data,
Right.
which is often much more abundant than labeled data,
Yeah,
to train our models.
it is. It's a rapidly evolving field with immense potential, opening up new possibilities for training more powerful and versatile models.
Okay, we've covered a lot of ground here, from the fundamental concepts of unsupervised learning to specific algorithms like clustering dimensionality reduction and anomaly detection,
Right.
and even advanced approaches like representation learning and self-supervised learning.
Yeah,
It's clear that unsupervised learning is a vast and fascinating field with incredible potential.
it is. And it's only going to become more important as we continue to grapple with the challenges of big data
Right.
and the need to extract insights from increasingly complex data sets.
All right, so we've laid the groundwork with perceptrons, MLPs, backpropagation, and activation functions.
Right.
Now let's step into the world of specialized deep learning architectures,
Okay.
starting with convolutional neural networks, or CNNs.
Okay.
I've heard so much about these, especially in image recognition.
Yeah.
What makes them so special?
CNNs are like the rock stars of computer vision.
Oh, wow.
They're specifically designed to work with data that has a grid-like structure, like images.
Okay.
Imagine a team of detectives,
Okay.
each focusing on a specific part of a crime scene photo.
Gotcha.
That's kind of how CNNs work.
Okay. I'm picturing these detectives,
Yeah.
each with their magnifying glass,
Uh-huh.
looking for clues.
Uh-huh.
But how do they actually break down the image and find these patterns?
They use these things called convolutional layers,
Okay.
which apply filters to the input image,
Right.
extracting local features like edges, textures, and shapes.
Okay.
Think of it like running a special magnifying glass over the image,
Right.
highlighting specific details.
So they're learning to see the
Yeah.
most important features in the image. That's pretty amazing.
It is. And then there are pooling layers,
Okay.
which essentially shrink down the size of the image,
Right.
making it easier to process
Uh-huh.
and more robust to small variations in the input.
Okay, so it's like summarizing the key findings of those detectives,
Okay.
right? Getting to the heart of the matter.
And finally, there are often fully connected layers at the end,
Okay.
which take all that processed information and use it to make predictions,
Right.
like classifying what's in the image.
Wow. So CNNs really are like these intricate detective teams
Yeah.
working together to analyze and understand images.
Yeah.
It's no wonder they're so good at things like image recognition.
They've revolutionized computer vision, achieving human-level performance on some tasks.
Wow, that's incredible.
Now let's switch gears and talk about recurrent neural networks, or RNNs.
Okay.
These are designed for sequential data like text or time series.
Okay, so if CNNs are the visual experts,
Right?
RNNs are the language and time specialists.
You got it.
Yeah.
RNNs have this amazing ability to process data that unfolds over time.
Hmm.
They have these special connections that allow information to persist from one step to the next,
Okay.
giving them a kind of memory.
So they can remember what they've seen before,
Right.
which helps them understand the context of the sequence.
It is. Think of it like reading a book.
Okay.
As you read each sentence.
Right.
You're not just processing the words in isolation,
Uh-huh.
but also building upon the understanding you gained from previous sentences.
Okay, that makes sense. But I'm noticing some more complex types of RNNs mentioned in the notes. So
Yeah.
like LSTMs and GRUs.
Uh-huh.
What are those all about?
You're right. LSTMs and GRUs are specialized types of RNNs
Okay.
that address some of the challenges that traditional RNNs face,
Right.
like the vanishing gradient problem.
Hmm.
They have more sophisticated memory mechanisms that allow them to store information for longer periods.
So it's like having a more reliable memory that can hold on to important details for longer. That seems crucial when you're dealing with long sequences of data.
Exactly. LSTMs and GRUs have become indispensable tools for natural language processing, speech recognition, and time series analysis.
This is also fascinating. It's like each of these architectures has its own unique way of
Yeah.
thinking and processing information.
It really is. And then we have attention mechanisms,
Okay.
which have become one of the most powerful innovations in deep learning.
Attention mechanisms. That sounds intriguing.
Imagine you're trying to translate a sentence from one language to another.
Okay.
You wouldn't just look at each word in isolation, right?
Right.
You'd pay attention to the surrounding words,
Yeah.
the context,
Mm-hmm.
to get the full meaning.
Right. The context is crucial for understanding.
Yeah.
So are you saying that attention mechanisms allow neural networks
Yeah.
to do something similar?
Exactly. Attention mechanisms allow the network to focus on the most relevant parts of the input when making predictions. It's like shining a spotlight on the most important information, allowing the network to process it more effectively.
That's incredible. So are these attention mechanisms used in a lot of different types of deep learning models?
They are. They're used in things like sequence-to-sequence models,
Okay.
which are great for tasks like machine translation,
Uh-huh.
and transformers, which are these incredibly powerful architectures that have taken the world of natural language processing by storm.
Okay. We've covered a lot of ground here, from perceptrons and MLPs
Yeah.
to CNNs, RNNs, and attention mechanisms.
Uh-huh.
It's amazing how diverse and specialized these deep learning architectures have become.
It is. And we're only scratching the surface.
Right.
There's so much innovation happening in this field, constantly pushing the boundaries of what's possible.
Now, these notes also talk about the importance of hands-on experience and research connections. It
Yeah.
seems like they're really emphasizing the practical side of machine learning.
Absolutely. You can't just learn about these concepts in a vacuum.
Right.
You need to get your hands dirty, experiment,
Mm-hmm.
build things.
Uh-huh.
That's how you solidify your understanding and develop the skills to apply these techniques to real-world problems.
So it's like learning to ride a bike. You can read all the manuals you want, but
Yeah.
you'll never truly learn until you actually get on the bike and start pedaling.
Exactly. And research connections are just as important.
Right.
Machine learning is a rapidly evolving field.
Mm-hmm.
So staying connected to the research community, attending conferences, reading papers,
Yeah.
it's all crucial for keeping up with the latest advancements.
It sounds like this post-grad ML course is designed to not just teach the fundamentals,
Right.
but to really cultivate a mindset of exploration, experimentation, and continuous learning.
It is. It's about empowering students to become not just skilled practitioners,
Right.
but active contributors to the field of machine learning.
Now, let's get back to the nitty-gritty of supervised learning.
Okay.
The notes provide a deeper dive into some of the core concepts we touched on earlier. I'm particularly intrigued by linear regression.
Okay.
What exactly is that?
Linear regression is a classic supervised learning algorithm that's used to predict a continuous output based on a linear relationship with one or more input features.
Right.
Think of it like trying to draw a straight line through a scatter plot of data points,
Oh, okay.
finding the line that best fits the data.
So if we have data on house prices and their corresponding square footage,
Yeah.
we could use linear regression to predict the price of a house based on its size.
Exactly. The algorithm learns a linear equation that describes the relationship between the input feature, which in this case is the square footage,
Okay.
and the output variable, which is the house price.
Uh-huh.
Then, given a new house's square footage, we can plug it into that equation and predict its price.
That makes sense.
What?
But what if the relationship between the input and output is more complex,
Yeah.
not linear?
Well, for those cases, we have other algorithms,
Hmm.
like logistic regression, which is particularly useful for predicting categorical outputs, often binary ones.
Binary outputs. Can you give me an example?
Sure. Imagine we're trying to predict whether a customer will click on an ad
Okay.
based on their demographics and browsing history.
Uh-huh.
That's a binary outcome. They either click or they don't.
So logistic regression would help us estimate the probability of a customer clicking on an ad
Exactly.
based on their characteristics.
It models the relationship between the input features and the probability of the output.
Okay.
belonging to a particular category.
Right.
Then we can set a threshold,
Uh-huh.
say 50%,
Right.
and classify anyone above that threshold as likely to click.
Okay, that makes sense. Now, what about decision trees?
Oh, yeah.
I remember seeing those mentioned earlier. They
Yeah.
sound pretty intuitive.
Decision trees are great. They're easy to visualize and interpret,
Right.
making them a popular choice for many applications.
Okay.
Imagine a flowchart where each node represents a decision based on a feature, and each branch leads to a different outcome or prediction.
So it's like a series of yes-no questions,
To be exact.
each one narrowing down the possibilities until we arrive at a final answer.
For example, if we're trying to predict whether a loan applicant is likely to default,
Okay.
we might start with a node that checks their credit score.
Uh-huh.
If it's above a certain threshold, we go down one branch.
Right.
Otherwise, we go down another.
And we keep branching until we reach a leaf node,
Right.
which gives us a prediction like likely to default or unlikely to default.
Right. That's right. Decision trees are particularly useful when we want to understand the reasoning behind a model's predictions.
Now let's talk about how we evaluate the performance of these supervised learning models.
Okay.
The notes remind us that accuracy alone can be misleading,
Yeah.
especially with imbalanced data sets.
Right.
Why is that?
Accuracy simply tells us the percentage of correctly classified instances,
Okay.
but it doesn't give us the full picture.
Right.
Imagine a data set where 99% of the instances belong to one class, okay,
Uh-huh.
and only 1% belong to the other.
Uh-huh.
A model that just predicts the majority class all the time would achieve 99% accuracy,
Right.
even though it's not really learning anything meaningful.
So it's like getting a perfect score on a test by just guessing C for every answer.
Exactly.
You might get lucky, but you're not demonstrating any real understanding.
So we need more nuanced metrics like precision recall
Mhm.
and the F1 score.
Okay.
Precision tells us, out of all the instances we predicted as positive,
Uh-huh.
how many were actually positive.
Okay.
Recall, also known as sensitivity,
Right.
tells us out of all the actual positive instances, how many did we correctly predict.
Gotcha.
And the F1 score is a kind of balance between precision and recall,
Right.
taking both false positives and false negatives into account.
Okay, so it's like having a more balanced scorecard that considers both the hits and the misses.
Exactly. And there's another metric called AUC,
Okay.
or area under the ROC curve,
Right.
which measures the model's ability to distinguish between classes across different thresholds.
These metrics sound crucial for understanding the strengths and weaknesses of our models
Yeah.
and for making informed decisions about which model to use for a particular task.
They are. They help us go beyond a single number, like accuracy,
Right.
and really understand how our models are performing in different scenarios.
And now let's circle back to representation learning
Okay.
and its impact on machine learning.
Yeah.
I remember earlier we talked about it as teaching machines to see patterns
Right.
we might not even notice ourselves. Can you elaborate on that?
Sure. Traditional machine learning relied heavily on manual feature engineering,
Right.
where experts would spend countless hours designing features for the model to learn from.
Yeah.
It was a time-consuming and often subjective process.
So it was like trying to teach a child to recognize a cat by describing its individual features.
Exactly.
Pointy ears, whiskers, tail.
But with representation learning, we've shifted to a more data-driven approach.
Okay.
The model learns to extract meaningful features from the raw data itself.
Gotcha.
Kind of like giving the child a bunch of pictures of cats and letting them figure out the defining features on their own.
That's a much more intuitive way to learn. No wonder the notes highlight this shift as a paradigm shift in the field.
It's a game changer.
Yeah.
We can now handle more complex data,
Right.
automate the feature engineering process,
Uh-huh.
and often achieve better performance than with traditional methods.
And deep learning, with its multiple layers of interconnected neurons,
Right.
has been a key driver of this revolution, right?
Absolutely. The hierarchical nature of deep neural networks allows them to learn increasingly abstract and complex representations of the data.
Okay.
It's like having a team of detectives, each specializing in a different level of detail,
Right.
working together to solve a case.
So the lower layers of the network might learn simple features like edges or textures,
Yeah.
while higher layers learn more complex features like shapes or objects.
Right.
It's like building up a hierarchy of understanding from the simple to the complex.
Precisely. And this ability to learn hierarchical representations has been instrumental in breakthroughs in fields like computer vision and natural language processing.
That makes sense. We see it all the time now with computers recognizing faces, translating languages, and even generating realistic-looking images.
It's truly remarkable how far we've come in such a short time.
Yeah.
And this is just the beginning. Now let's talk about something that's equally important,
Okay.
data quality.
Right.
It's a topic that comes up again and again in these notes.
Yeah.
Why is that?
Well, it's like that old saying, garbage in, garbage out, right?
Exactly.
No matter how sophisticated our algorithms are, they can't perform miracles with flawed or biased data.
The quality of the data we feed our models is paramount.
Right.
We need to be acutely aware of potential pitfalls in our data and take steps to ensure its quality and integrity.
So what are some of the key things we need to look out for?
Okay.
I've heard the term data bias mentioned a lot. What exactly is that, and why is it so important to address?
Data bias can creep in from various sources,
Okay.
and it can lead to unfair or discriminatory outcomes if we're not careful.
Right.
Imagine we're training a model to predict loan approvals,
Okay.
but our historical data reflects existing biases in the lending system.
Right. So if the data shows that certain groups of people were historically denied loans at a higher rate, our model might learn to perpetuate those biases,
Right.
leading to unfair denials for those same groups in the future.
Exactly. It's crucial to identify and mitigate these biases
Right.
to ensure our models are fair and equitable.
That makes sense. What about class imbalance? I remember seeing that mentioned as well.
Class imbalance is another challenge.
Okay.
It occurs when one class in our data set has significantly fewer instances than the others. This can skew the model's learning,
Right.
leading to poor performance for the minority class.
Can you give me an example of that?
Sure. Imagine you're training a model to detect fraudulent transactions. Only a tiny percentage of transactions are actually fraudulent.
Right.
If we don't address this class imbalance, our model might simply learn to classify everything as not fraudulent, missing those rare but crucial cases.
Wow, that's a big problem. So how do we handle class imbalance?
There are several techniques we can use, such as oversampling, where we create copies of instances from the minority class to balance the data set.
Right.
Undersampling, where we remove instances from the majority class.
Okay.
And cost-sensitive learning, where we assign different costs to misclassifications, giving more weight to errors on the minority class.
It sounds like there's a whole toolkit of techniques
There is.
for tackling these data quality challenges.
Data preprocessing, cleaning, and transformation are essential steps in the machine learning pipeline.
Right.
It's all about preparing the data to ensure that our models are learning from the best possible information.
These notes also highlight the importance of understanding the software and hardware landscape. For modern machine learning, I know there are a lot of different frameworks and platforms out there. Can you break it down for me?
Sure. Popular ML frameworks like TensorFlow and PyTorch are essential tools for creating and training our models.
Right.
Think of them as the building blocks for our machine learning projects.
Okay.
Each framework has its own strengths and ecosystem of libraries and tools.
So it's like choosing the right set of tools for a particular construction project.
Exactly. TensorFlow, developed by Google, is known for its scalability and production readiness, making it a popular choice for large-scale deployments.
Okay.
PyTorch, developed by Facebook, is known for its flexibility and research friendliness,
Right.
which makes it a favorite among researchers.
And then we have these powerful cloud computing platforms like AWS, Google Cloud, and Azure, which provide the computational muscle to train these complex models, right?
Right. These platforms have truly democratized access to the computational power needed for modern machine learning. They offer a wide range of services, including computing resources, data storage, pre-trained models, and specialized hardware like GPUs and TPUs.
It's amazing how these tools and platforms have made machine learning more accessible than ever before.
It truly is. The barriers to entry continue to lower.
Right.
And that's incredibly exciting. Now let's talk about optimization and generalization.
Okay.
Two essential concepts for building effective machine learning models.
Optimization and generalization.
Yeah.
These terms have come up a few times already. Can you remind me what they're all about
and
why they're so important?
Of course. Optimization is all about finding the best possible set of parameters for our model.
Right.
Think of it like trying to find the lowest point in a vast landscape.
Okay.
We need to navigate that landscape efficiently and find the parameters that minimize the error on our training data. Generalization, on the other hand, is about ensuring that our model performs well on unseen data.
Right.
That it can generalize its learning to new examples.
So optimization is about fitting the model to the data we have.
Right.
While generalization is about making sure it doesn't overfit and can handle new data it hasn't seen before.
Precisely. It's a delicate balancing act.
Okay.
We need our models to learn from the data we have, but not become so specialized that they fail to generalize to new situations.
That makes sense. Now, what about gradient descent? I've
Yeah.
heard that term a lot.
Yeah.
What is it, and how does it relate to optimization?
Gradient descent is a fundamental algorithm for optimization. Imagine you're a hiker trying to find the lowest point in a valley.
Okay.
You might start by looking around and taking a step in the direction of the steepest descent.
Right.
That's essentially what gradient descent does.
Gotcha.
It iteratively updates the model parameters in the direction that minimizes the loss function.
So it's like taking small steps down the hill until we reach the bottom,
Yeah.
which represents the optimal set of parameters.
Exactly. But sometimes basic gradient descent can be a bit slow, or it might get stuck in local minima values that aren't the absolute lowest point.
So what do we do about that?
That's where variations like stochastic gradient descent, SGD,
Okay.
momentum arms drop, and atom come in.
Right.
They introduce clever tweaks to the basic algorithm to speed up convergence and avoid getting trapped in those local minima.
Can you give me an analogy for those variations?
Sure. Imagine a ball rolling down a hill.
Okay.
Momentum gives it an extra push,
Okay.
allowing it to roll over small bumps and keep moving even when the slope flattens out. Armstrong and Atom are like intelligent hikers who adjust their step size based on the terrain,
Right.
taking larger steps on flat ground and smaller steps on steep slopes.
Those are great analogies. Now, what about regularization techniques? I remember hearing that they're important for preventing overfitting
Yes.
and improving generalization.
You're right. Regularization is like adding a penalty term to our model's objective function,
Okay.
discouraging it from learning overly complex functions
Uh-huh.
that fit the training data too closely,
Right.
but might not generalize well to new data.
So it's like adding a bit of friction to the ball rolling down the hill,
That's a great way to think about it.
preventing it from going too fast and overshooting the bottom.
There are several regularization techniques,
Okay.
such as L1 and L2 regularization, which add different types of penalties to the model parameters,
Right.
and dropout, which randomly drops out some neurons during training,
Right.
forcing the network to learn more robust features.
And what about this bias variance trade-off I keep hearing about?
Yeah,
It sounds like a tricky balancing act.
it is. Bias refers to the error introduced by simplifying assumptions made by the model,
Okay.
while variance refers to the error introduced by the model's sensitivity to small fluctuations in the training data.
So a high bias model is too simple and underfits the data,
Right.
while a high variance model is too complex and overfits the data.
Exactly.
It's like finding the sweet spot between being too rigid and too flexible.
We want our models to capture the underlying patterns in the data
Right.
without getting bogged down by the noise.
Okay.
Techniques like cross-validation and ensemble methods can help us strike the right balance.
Okay, so it's all about building models that are good at learning,
Yeah,
but also good at generalizing to new situations.
precisely. Now, are you ready to dive into the fascinating world of unsupervised learning?
Absolutely. I'm excited to uncover some of those hidden treasures.
Well, then let's start with clustering,
Okay.
which is all about grouping similar data points together based on their inherent characteristics.
Right.
Imagine sorting a jumbled box of objects into meaningful categories based on their similarities.
Okay.
That's essentially what clustering algorithms do with data.
It sounds like a fun puzzle. So how do these algorithms figure out how to group the data
Right.
without any labels to guide them?
There are several different approaches.
Okay.
K-means is a classic algorithm that partitions the data into K-clusters, where each data point belongs to the cluster with the nearest mean or centroid.
Right.
It's a simple and efficient algorithm,
Okay.
but it has its limitations.
Okay.
It assumes that the clusters are spherical,
Right.
which might not always be the case.
So what if the clusters have more complex shapes?
That's where algorithms like hierarchical clustering and DBSCAN come in.
Okay.
Hierarchical clustering builds a tree-like structure of clusters,
Right.
allowing us to see how the data points relate to each other at different levels of granularity. DBSCAN, or density-based spatial clustering of applications with noise,
Wow.
is another powerful algorithm that can discover clusters of arbitrary shapes
Okay.
and even identify outliers,
Right.
data points that don't really belong to any cluster.
And how do we know if we've done a good job clustering our data?
There are various evaluation metrics,
Okay.
but one commonly used metric is the silhouette score,
Right.
which measures how similar a data point is to its own cluster compared to other clusters. A higher score generally indicates a better clustering,
Okay.
where data points are tightly grouped within their clusters
Right.
and well separated from other clusters.
Okay, so clustering is all about finding those hidden groupings in our data.
Yeah.
But what about dimensionality reduction?
Right.
That's another key concept in unsupervised learning.
Dimensionality reduction is all about simplifying our data.
Okay.
By reducing the number of variables or features while preserving the most important information.
Right.
Think of it like creating a simplified map of a complex terrain,
Okay.
highlighting the key landmarks and features without getting bogged down in every little detail.
So it's like creating a more manageable and interpretable representation of the data.
Exactly.
Yeah.
And it's essential for several reasons.
Okay.
For one, it can make it much easier to visualize high-dimensional data.
Right?
It can also reduce computational complexity, making our algorithms run faster.
Right.
And it can help mitigate the curse of dimensionality, which refers to the challenges that arise when working with data that has too many features.
Can you give me some examples of dimensionality reduction techniques?
Sure. PCA, or Principal Component Analysis,
Okay.
is a classic technique that finds the directions of maximum variance in the data
Right.
and projects the data onto a lower dimensional subspace.
Okay.
It's like finding the most informative axes along which the data varies the most.
And then there are more advanced techniques like TSNE and UMAP,
Yeah.
which are particularly good at preserving local similarities between data points, right?
Exactly. They're like creating artistic renditions of complex data landscapes,
Okay.
highlighting clusters and relationships that would otherwise remain hidden in a sea of dimensions.
Dimensionality reduction sounds like an incredibly powerful tool.
It is.
It's like bringing order to chaos, helping us make sense of complex data
Right.
and uncover hidden patterns.
Now let's talk about another fascinating aspect of unsupervised learning:
Okay.
anomaly detection. It's all about identifying those data points that deviate significantly from the norm,
Okay.
those outliers that might signal something interesting or unusual.
So it's like being a detective looking for clues that something is out of place.
Exactly. Anomaly detection is used in a wide range of applications,
Right.
from fraud detection and cybersecurity to system monitoring and medical diagnosis.
Can you give me some examples of how anomaly detection is used in practice?
Sure. In fraud detection,
Okay.
anomaly detection algorithms can help identify unusual spending patterns or transactions that might indicate fraudulent activity.
Right.
In cybersecurity, they can help detect intrusions or malicious behavior on a network.
Okay.
And in medical diagnosis, they can help identify patients who might have a rare disease or condition.
It sounds like anomaly detection plays a crucial role in keeping systems safe
It does.
and identifying potential problems early on.
Now let's circle back to representation learning
Okay.
and talk about a specific type of neural network that's become a key player in this field:
Okay.
autoencoders.
Okay, autoencoders. We touched on these earlier.
Yeah.
They're all about learning meaningful representations of the data, right?
Yeah.
Can you break down how they actually work?
Sure. Think of an autoencoder as a machine that learns to compress and decompress information.
Okay,
It consists of two parts:
gotcha.
an encoder and a decoder.
Okay,
The encoder takes the input data and maps it to a lower dimensional latent representation,
right.
kind of like creating a condensed version of the information.
Uh-huh.
Then the decoder takes that latent representation
Right.
and tries to map it back to the original input space,
Okay.
effectively reconstructing the input.
So it's like taking a complex image,
Yeah.
encoding it into a smaller, more compact representation,
Right.
and then decoding it back to the original image.
Exactly. And by training the autoencoder to reconstruct its input, we're essentially forcing it to learn
Right.
a compressed and meaningful representation of the data.
That's really clever. It's like teaching the machine to find the essence of the information
Yeah.
and represent it in a more efficient way. I remember seeing different types of autoencoders mentioned in the notes, under complete denoising and variational. What's the difference between them?
You're right. There are different flavors of autoencoders,
Okay.
each with its own unique characteristics and applications.
Right.
Under complete autoencoders, force the network to learn a compressed representation by having a lower dimensional latent space than the input. It's like trying to fit a lot of information into a smaller suitcase.
Right.
You have to be selective about what you pack.
So it's like forcing the network to learn the most salient features,
Exactly.
the ones that are essential for reconstructing the input,
Then we have denoising autoencoders.
which are trained to reconstruct the input from a corrupted version.
Right. It's like learning to read a text message with typos.
Oh, yeah.
Have to learn to ignore the noise and focus on the underlying message.
That's a great analogy. So denoising autoencoders learn to extract robust features that are less sensitive to noise or variations in the input. What about variational autoencoders?
Variational autoencoders are a bit more complex.
Right.
They learn a probabilistic latent representation,
Hmm.
which means that they're not just learning a single representation, but a distribution of possible representations.
Okay.
This allows us to generate new data samples that resemble the original data.
Wow, that's really cool. So it's like learning the underlying structure of the data,
Yeah.
the rules that govern how the data is generated.
Exactly. Variational autoencoders have become powerful tools for generative modeling,
Right.
allowing us to create new images, text, music, and even more.
Autoencoders seem incredibly versatile. They can be used for dimensionality reduction, feature extraction, anomaly detection, and even generative modeling. It's amazing how a single architecture can be adapted for so many different tasks.
It is. And they're just one example of the incredible power of representation learning. Now let's talk about another fascinating approach that leverages unlabeled data for representation learning, self-supervised learning.
Self-supervised learning. That sounds intriguing. It sounds like the model is somehow teaching itself.
In a way, it is. Self-supervised learning is a clever way to train models without relying on explicit labels. We essentially create pretext tasks that force the model to learn meaningful representations from the data itself.
So it's like we're giving the model a puzzle to solve, and in the process of solving it, it learns something useful about the data. I remember the examples you gave earlier, contrastive learning and masked language modeling.
Exactly. In contrastive learning, we train the model to distinguish between similar and dissimilar data points. Kind of like showing a child two pictures and asking them whether they're the same or different.
Right.
By doing this repeatedly, the child learns to recognize the features that distinguish different objects.
And in masked language modeling, we hide some words in a sentence and train the model to predict the missing words. This forces the model to learn about the relationships between words and the context in which they appear.
Precisely. These self-supervised tasks encourage the model to learn about the underlying structure and relationships within the data, even without explicit labels.
Self-supervised learning sounds incredibly powerful. It allows us to leverage vast amounts of unlabeled data, which is often much more abundant than labeled data, to train our models.
It is. It's a rapidly evolving field with immense potential, opening up new possibilities for training more powerful and versatile models.
Okay, we've covered a lot of ground here, from the fundamental concepts of unsupervised learning to specific algorithms like clustering dimensionality reduction and anomaly detection, and even advanced approaches like representation learning and self-supervised learning. It's clear that unsupervised learning is a vast and fascinating field with incredible potential.
It is. And it's only going to become more important as we continue to grapple with the challenges of big data and the need to extract insights from increasingly complex data sets.
It feels like every corner we turn in machine learning leads to even more fascinating discoveries. It's like exploring a vast, uncharted territory with endless possibilities.
It really is. And that's what makes this field so exciting. There's
Mhm.
always something new to learn, always new challenges to tackle.
Hmm.
So are you ready to explore some of those uncharted territories, those cutting-edge advancements that are shaping the future of machine learning?
Absolutely. Lead the way.
Well, one of the things that really stands out in these notes is this push to move beyond just making predictions to actually understanding causality. It's a fundamental shift in thinking.
I remember you mentioned this earlier. We talked about how correlation doesn't necessarily equal causation. Just because a model finds a strong association between two things doesn't mean one causes the other.
Exactly. Think back to our ice cream and sunburn example.
Oh, yeah.
A model might tell us that there's a strong correlation between ice cream sales and sunburn cases.
Right?
But that doesn't mean eating ice cream causes sunburn. They're both likely related to a third factor, sunny weather.
Right. So how do we move beyond these superficial correlations and start uncovering true causal relationships?
It's a challenging but incredibly important area of research. There are a few different approaches being explored. One involves incorporating domain knowledge and causal assumptions into our models, essentially giving them some guidance about how the world works. Another approach involves designing experiments that allow us to manipulate variables and observe their effects, much like scientists do in controlled experiments.
So it's about understanding not just what happens, but why it happens, right?
Exactly. And this understanding of causality has the potential to revolutionize fields like healthcare economics and social science. Imagine being able to not just predict which patients are at risk for a certain disease, but also identify the specific factors that contribute to that risk, allowing for more targeted and effective treatments.
That would be incredible. It feels like we're moving from a world of just observing patterns to a world where we can understand and potentially manipulate the underlying mechanisms.
You're exactly right. It's a powerful shift in perspective. Now, another theme that's emerging in machine learning is this increasing emphasis on interpretability. As models become more complex and powerful, it becomes increasingly important to understand how they arrive at their predictions. That makes sense. If we're going to trust these models to make important decisions, especially in fields like healthcare finance and criminal justice, we need to be able to understand their reasoning process.
Precisely. And this need for interpretability is driving a lot of research into new techniques for explaining black box models. Remember earlier when we talked about SHP values and Lyme? Those are just two examples of techniques that can help us peek inside those black boxes and understand how individual features contribute to a model's predictions.
It feels like this pursuit of interpretability is going to be crucial for building trust in machine learning systems and for ensuring that they're deployed responsibly.
Absolutely. Transparency and accountability are essential if we want these powerful technologies to be accepted and used for good. Now, another area that's getting a lot of attention is robustness. Robustness. What does that mean in the context of machine learning?
It's about building models that are resilient to noise errors and even adversarial attacks. It turns out that even highly accurate models can be surprisingly brittle. There are these things called adversarial examples,
Okay.
carefully crafted inputs designed to trick the model.
So even a model that performs flawlessly on a standard benchmark might completely break down when faced with one of these adversarial attacks.
Exactly. And that's a big problem, especially if we're going to rely on these models in safety-critical applications.
So how do we make our models more robust?
There are a few different approaches. One is adversarial training, where we expose the model to these adversarial examples during training, forcing it to learn more robust features. Another approach is to incorporate uncertainty estimation into our models, allowing them to flag inputs that they're not confident about.
It sounds like building robustness into our machine learning systems is going to be crucial for ensuring their reliability and safety in the real world.
It absolutely is. As these systems become more integrated into our lives, we need to be confident that they can handle unexpected inputs and adversarial attacks gracefully.
This all makes a lot of sense. It's not just about accuracy anymore. It's about building models that are reliable, interpretable, and robust. Now, one of the terms that really caught my eye in the notes is meta-learning. It sounds futuristic.
It is pretty futuristic. Meta-learning is essentially about teaching machines to learn how to learn.
So instead of training a model for a specific task, we're training a model that can learn to perform any task.
That's the general idea. Meta-learning algorithms are trained on a variety of tasks, and they learn how to adapt quickly to new tasks with minimal data. It's like giving a student a set of study techniques that can be applied to any subject, allowing them to learn new material more efficiently.
That's fascinating. It seems like meta-learning has the potential to really revolutionize how we build and deploy machine learning models.
It does. It could lead to more adaptable and versatile AI systems that can learn new things with minimal human intervention.
Another area that I find particularly interesting is the intersection of machine learning with other fields like neuroscience and cognitive science. It seems like there's a lot of potential for cross-pollination of ideas.
Absolutely. There's this growing recognition that we can gain valuable insights into both artificial and natural intelligence by studying how the brain works. Neuroscience can inspire new architectures and algorithms for machine learning, while machine learning can provide tools for analyzing and understanding brain data.
It feels like we're on the verge of a new era of understanding intelligence, both artificial and biological.
It's a truly interdisciplinary endeavor that holds immense promise for unlocking the mysteries of the mind and creating more intelligent and capable machines.
Wow, this has been an incredible journey. We've covered so much ground from the fundamental concepts of machine learning to the cutting-edge advancements that are shaping the future of this field. It's clear that machine learning is not just a technology, but a force that's transforming our world in profound ways.
It is. And it's important to remember that this is just the beginning. There's so much more to explore, so much more to discover.
Well, there you have it, folks, a deep dive into the fascinating world of machine learning. We've explored the foundations, the cutting-edge advancements, and even touched on the ethical considerations that come with this powerful technology.
Remember, machine learning isn't just about building intelligent machines. It's about augmenting human intelligence. solving some of the world's most challenging problems, and ultimately shaping a future where technology empowers and benefits humanity as a whole.
So keep learning, keep exploring, and keep asking those big questions. Who knows, maybe you'll be the one to make the next breakthrough in this incredible field. Until next time, keep diving deep.